Assalamu alaikum students. Welcome to another lecture of Slate. This is me, Khawaja Yasin. Let's study chemistry. When we talk about O-levels chemistry, the chapter of chemical energetics is very important because you can get discussion-based questions, you can get calculation-based questions, or you can just get definitions out of these questions. This chapter also contains energy profile diagram, just to label it. So this chapter has various types of things. As you can see in the course outline, we will be talking about endo and exothermic reactions. We will be talking about the energy profile diagram. We will be talking about the enthalpy change. What is enthalpy? What is enthalpy change? We will be talking about the activation energy. We will also be talking about the energy profile diagram. And lastly, the bond energy calculation, the bond making and the bond breaking. So let's start talking about chemical energetics. So in chemical energetics, we talk about the change or the energy involved in a chemical reaction. So chemical energetics deals with the energy involved in a chemical reaction. Energy can come in the system, energy can leave the system. It can either enter or exit. On that very basis, we have two types of reactions. The first one is the endothermic reaction. And the other one is the exothermic reaction. Now, it is not just the entry or exit of heat. We have to understand the idea of temperature change in the surrounding. So what is the surrounding and what is the system? So in the case of endothermic, we'll deal with that later. The energy absorbs or is required or is needed. You can get any of these terms in the exam. The energy is absorbed, required, or needed by the reactants to proceed forward. So in this case, the reactants will absorb energy and only then they can become products. So reactants, when we proceed, energy is absorbed. And only then it becomes products. So energy is absorbed or added in the system. From where? From the surrounding. And exothermic, it's the exact opposite. The energy is released by the reactants to proceed forward. It's the exact opposite. So reactants have a particular energy and they will give it out. When the energy is gone out, only then they become the products. So students, that is what we have. But as I said, the reactants in the case of endothermic, when the reactants absorb energy, they become products. So if I just make a normal energy profile diagram, that's not the final one, just know that. If this is the energy profile, and for energy profile, on x-axis we take energy, on y-axis we take energy, on x-axis It's the progress of reaction. So know for sure, students, reactants absorbed energy and then became products. So reactants have lower energy than the products. Reactants have energy lower than the products. So if I place my reactants here in the energy level, the energy is increasing upwards. The products will be on a higher level of energy here, because energy was absorbed by the reactants. And when we talk about the exothermic, where the energy was released, in the case of exothermic reaction, students, the reactants have energy higher than the products. Why? Because reactants give out energy and then they become products. So if I make reactants here, the products will come here. You can see there is a decline in energy. Even here. In the case of exo, the energy from the reactants to product, it's decreasing because you're giving out energy. And in the case of endothermic, the reactants have a lower energy and the products have a higher energy. So that's one thing. Now, the two concepts. We will come back to this diagram later. We'll add a lot more here. But before that, system versus surrounding. What is a system? System is where the reaction is taking place. And surrounding is obviously the surrounding around it. Now, there is always a confusion among the students. If I tell you that this is a beaker and we have a reaction going on between, if you can say, calcium and chloride ions. Just assume that's the reaction going on. And all of it is an aqueous solution. For instance, it's an aqueous solution and the reaction is taking place this way. So students, the whole of the solution is not the system. Remember, the whole of the solution is not the system. The system is just this part, where calcium is reacting with chloride. That's the system. And the blue part, the water, and even the external side of the beaker, that's the surrounding. So, in the case of endothermic reaction, the heat is absorbed in the system from the surroundings. Now, as a result, if the system is taking in heat, energy from the surrounding, there will be a drop of temperature in the surrounding. So if I put a thermometer here, for instance, there's a thermometer here. That's a thermometer. Now, in the case of endo, this system got the heat. The heat entered here. So there will be a drop in temperature of the surrounding because surrounding gave its own heat to the system. So as a result, the temperature of the surrounding decreases. And likewise, when we talk about the exothermic reaction, in the case of exothermic, the heat is released into the system, into the surrounding, by the system. So the temperature of the surrounding will definitely increase. So the temperature of water, in this case, the solution, will increase. So that is the concept about system and surrounding. In the case of exothermic, the temperature of the surrounding will increase, and surrounding is even the solution, water, aqua solution, and the surrounding outside as well. So that's what we know about these. Now, when we talk about chemical energetics, we need to keep in mind something about the kinetic particle theory. That will help you understand the concept. Let's talk about two reactions very common in daily life. Water turning into ice and ice turning into water. Now, these are two different reactions. Obviously, it's the same reversible reaction. But what do we know about water? The particles, if we talk about the particles, particles are moving. If the particles are moving, which means they have kinetic energy. But in the case of ice, they are in a fixed position. So the energy is lost, right? Energy is lesser as particles only vibrate. Let's just talk about particle theory and then we'll have a comparison. In the case of ice, again we know lesser energy, and water has free moving particles, so water has higher energy. So what do you do if you have to convert ice into water? Will you give heat or will you take out heat from the system? Obviously, in order to melt ice, you need to add heat. So this would be an endothermic reaction. As we have added heat in the system and the reactants had a lesser energy and the products had a higher energy. And from water to ice, water particles will release energy because they have to stabilize in the ice structure. So this would be exo. So just comparing this with what we had here. In the endo, reactant had a lesser energy, product had a higher energy. And that's what we did. In the case of endo, reactant has a lesser energy, product has a higher energy. So that's just reiterating the fact. But in this chapter, we will not talk about the energy change by the usage of term energy. We will, on the other hand, talk about enthalpy. What is enthalpy? Enthalpy is the heat content. For instance, enthalpy of reactant here is just a different term for energy. That's what you need to understand. But in the case of heat, so enthalpy of reactant, which is ice, is lower, lesser energy, lesser enthalpy. Enthalpy of product, which is water, is higher. Reactant is lesser, product is higher. So that is the enthalpy. But again, in a reaction, we will not just talk about enthalpy. We would rather talk about Enthalpy change. Enthalpy is denoted by letter H and it has the unit of kilojoules per mole. So what is enthalpy change? Enthalpy change will be delta H. Delta is because of the change in enthalpy. The change that is occurring from reactant to product. And what is enthalpy change? The change in enthalpy from reactants to products. So we have two types of reactions. Again, endothermic, exothermic. So in the case of endothermic reaction, the energy is being added. The change of the system, since the energy is coming in, we are adding the energy, we are not losing energy. If the energy is getting added in the system, as the heat is added in the system, enthalpy of the system increases. Obviously, enthalpy of the whole system increases. And due to that fact, for endothermic reaction, the enthalpy change value is always positive. For endothermic, the enthalpy change is always positive. And vice versa. For exothermic, as the energy is leaving the system, we are losing energy. We are losing the bank balance. So we are in negative. So for exothermic, enthalpy change is always a negative value. So that's a fixed rule, students. That is a fixed rule. So let's look at this diagram. Now in this case, as I said, we'll be adding more things in this particular diagram. Since the energy is increasing, this is the endo, and this is exothermic. And as I said, in the case of endothermic, energy of the system is increasing. It's going from reactant to product. So the arrow will be upwards. So since that is the enthalpy change of the system, it's increasing upwards. And since it's the difference between reactant and the product, enthalpy change, it's a positive value. And in the case of exothermic, it is decreasing downwards. The reactant had a specific enthalpy and it's getting lower. So the arrow will come downwards. And in this case, you have to label it as well. Enthalpy change is negative. So that is what we know. Now, as I said, the diagram is still empty. There is a lot more to be added. Not a lot more, just one more thing. And that, students, is called activation energy. EA. Now, many of you drive cars. So when we talk about cars, why do we ignite? We spark the fuel. We don't keep it burning throughout. We just spark ignition so that we just give it a particular energy to start. When the engine starts, we just give it a particular energy by giving it ignition. So we've just activated the engine and the car will start moving using minimum fuel. That's what activation energy is. Activation energy is the energy required by the reactants to start a reaction. So if you don't provide your reactants with the activation energy, your reaction is not going to be started. So A, it's required. B, that too by the reactants. These two are important things to remember. Activation energy. So why have I highlighted the part that it's required? Since it's required, it's needed, it's absorbed. Activation energy is always endothermic. Always. So, positive sign. Be it an endothermic reaction, be it an exothermic reaction, activation energy is always endothermic. Reactants, on the other hand, they're always needed by the reactants, because in order to start the reaction, we start off from the reactants. So it is always energy more than the energy of the reactants. So in this energy profile diagram, let's complete this diagram. So in the case of exothermic, reactants are already on a higher energy, but it's not the fact that if there are two reactants present, they will just start reacting. They'll start reaction. No. You have to provide it with a specific amount of energy, which is higher than the energy of the reactants. So there will be a parabola. We will see such a curve which will move upwards from the reactants and then downwards to the product. From reactant to product, that was just the enthalpy change difference. This one. But now this shows the activation energy. So how much is the activation energy, students? As I said, energy needed, so it's endo, and by the reactants. So they will start off from the reactants, not from the products. So the arrow will go upwards from the reactants. That's activation energy, and that's always positive. In the case, this was exothermic. The reactants had a higher energy. But in the case of endothermic, again we'll move upwards and then backwards to the products. That is what it is. In this case, we started the energy, activation energy from this level. But here, we will not start it from this level because this is the level of energy level of products. As I said, it is always the energy required by the reactants. So we will start it from the point of the reactants. So this again is activation energy, and this is a positive value. So these two are the energy profile diagrams, students, for both endo and exothermic reactions. In the exam, you have 4 to 5 mark question. They'll ask you to label the axis. They'll ask you to label the reactants and the products. They'll ask you for the energy level, obviously. There is a different energy level for exo. There's a different energy level for endo. Then they'll ask you for the enthalpy change arrow. They'll ask you for the activation energy arrow. 4 to 5 marks, free of cost. That's why it's a good chapter, an important chapter. Now, after the activation energy, we'll just talk about an important concept of bond making versus bond breaking. These two are two different concepts. Two different energies are involved. Not actually different, they're actually the same. But there is always a confusion among the students. Because one of the values is endo, one of the values is exo. How will you remember it? When I was a student, how did I remember it? I have to break this pencil. I won't. I would never break my pencil because that is a loss for me. That is a loss for you. We won't be able to record more lectures. But again, if I have to break this pencil, do I have to give energy or it will just break automatically and give out energy? I have to give energy to break. In order to break something, you always have to give energy. So if you're giving energy, bond breaking, you need to give energy for breaking. So bond breaking is always endothermic. And just like ice particles, we're forming bonds. So I've broken it into pieces. And they're just randomly moving here and there. So they have gained kinetic energy. I gave energy so that they can release from the bond. Now the atoms are moving freely, here and there, here and there, here and there. But then I have to contain them again. I have to make a bond. So do I have to give energy to make a bond? Or since they had higher kinetic energy, I take energy out of them and I fix them in a bond. So in order to make a bond, we take energy out. Because the particles, the free atoms have a higher energy, they are moving freely. But when we have to contain it, energy is taken out, energy is lowered. So bond making or bond formation, that term is also used sometimes, is always exothermic. So that it is always exothermic. So bond making is a negative value, bond breaking is a positive value. In any chemical reaction, bond breaking and bond making for a particular bond will always be the same. So if we have a carbon-hydrogen bond, so there is a particular bond energy. What is bond energy? It is the energy needed to make, or in your case, or break a bond. Bond energy values do not need to be negative or positive. They're always a particular value. We'll just make them negative or positive according to, if we are using it to break, that's a positive value. If you're using it to make, that's a negative value. But every particular bond, if there is a CH bond has its own particular value. If there is an OH bond, it has its own particular value. So every bond has its own particular value of bond energy. That's up to us if we are going to make it or break it. Make it or break it. Now, we see both bond making and bond breaking during the course of a reaction. For instance, we have reactants and then we have products. Let's take a very basic example of hydrogen plus oxygen making water. Now, hydrogen, look at hydrogen. One hydrogen has a single bond. So let me tell you one thing. In order to solve these questions, you need to have a good grip on chemical bonding. You can see it on our YouTube channel, the lecture of chemical bonding. How do these compounds are formed? What type of bonds do they make? Do they make positive single bonds, double bonds, triple bonds? That is for you to know with the knowledge of chemical bonding. So we have two hydrogen bonds because there are two. We have one. Now that is from the knowledge. Oxygen makes a double bond between two oxygen atoms. There is a double bond, students. So this is OO. In the case of water, that's water. But initially, I just cannot mix these up. I have to first break the bonds. Broken this bond with whatever the energy of hydrogen bond energy is. Broken this bond. So twice of that energy. Broken this double bond. Now we have something. So in the products, in the reactants, we are always breaking the bonds. Because just like if you have to make a milkshake, you first cut the bananas into pieces, then you mix it. So in this case, the reactants have to be broken down. Their bonds have to be broken down. So for the reactants, it's always bond breaking. Now, in order to become the product, one oxygen will make a bond with this hydrogen and this hydrogen. The other one will make a new bond with this hydrogen and this hydrogen. So new bonds are being made so that two waters are made. So in order to make products, we have bond formation. So remember, students, the reactants undergo bond breaking. Products undergo bond formation. That's important. Now, let's look at another reaction, a very common one in the exam. You will be provided with the bond energy values. Even I don't remember them, that's why. So don't worry about that. Let's do a hypothetical question where the bond energy values will not be given, but we need to understand the concept. Let's see. Let's burn methane in oxygen. We get carbon dioxide and 2 moles of water, 2 moles of oxygen. So that's what it is, students. With this equation and the reaction, I've been given various bond energies values. And bond energy values are also in kilojoules per mole. So we have a bond energy of CH. We have a bond energy of oxygen single bond. We have a bond energy of oxygen double bond. We have a bond energy of carbon and oxygen single bond. A bond energy of carbon oxygen double bond. Bond energy of oxygen hydrogen single bond. Now let me tell you, most of the times it's not that way, but a few times in the past papers, the examiner has given you irrelevant bond energies. Irrelevant. So you need to know which ones are to be skipped out. For instance, as I said, you need to know chemical bonding. You need to know the structure. Sometimes they've given you the structure, making your life hell easy, students. So in this case, there are no structures. But we know from chemical bonding, how does a methane structure looks like? Carbon makes 4 single bonds with hydrogens. So we'll use this bond energy into 4. Now, in this case, do we use oxygen single bond or double bond? In this question, we talked about that how oxygen makes a double bond, not a single bond. This is a wrong value. It can be given just to confuse you. No need of oxygen single bond value. So here we have, it's better to make the number of moles because there are 2 oxygens, so make it 2 that way so that you never make a mistake. So how many oxygen double bonds do we see? 1, 2. So I will multiply this value by whatever the value is by 2. We have the bond energy values given along with it. We'll just solve a question after this. Now let's look at this one. Carbon dioxide. Again, the knowledge of chemical bonding. Let me recall. That's carbon. 1, 2, 3, 4. And oxygen has a valency of 2. So all of them have now 8 electrons. So since there are 2 pairs So carbon and oxygen have a carbon-oxygen double bond. Hence, this carbon-oxygen single bond value is also irrelevant. And now how many carbon-oxygen bonds do we see? 1, 2 in one molecule. So that would be 2 into carbon and oxygen value. Plus, let's look at water. HOH. So in this case, how many oxygen-hydrogen bonds do we see, students? 1, 2, 3, 4. So that is why this value will be multiplied by 4. Now this is what you need to do. First, it's a 3 to 4 mark question. You calculate the energy associated with bond breaking. You just write these here, you put the values given and you get the answer, whatever the answer is. Then you make another one, the energy associated with bond making. You put the values here. Second step. Now, how to calculate the enthalpy change here? How to calculate? This is just the half of the question. In order to calculate the enthalpy change, it is always reactants, total enthalpy of the reactants minus enthalpy of the products. Sometimes students have a confusion. Sometimes they put products before and reactants later. How to memorize that? As I said, reactants, they undergo bond breaking. So bond breaking is always endo, and hence this always needs to be a positive value. On the other hand, products, bond formation, exo. So this is always a negative value. But if you memorize this equation, you will never make a mistake, but sometimes students do forget. So students, that is what this whole chapter is about. Endothermic, exothermic. So we talked about the exothermic and endothermic reaction. We talked about the temperature of the surroundings. We talked about endothermic against surroundings. Enthalpy change for exo and endo. We talked about that. Activation energy, minimum energy needed. The colliding part we'll discuss in the next chapter, which is the rate of reaction. Draw, label, interpret, rate of reaction, reactants, products, enthalpy change, activation energy. We did that. Bond breaking is endothermic, bond making is exothermic, and explain the enthalpy change of reaction. That's what we just did. Calculate the enthalpy change using the bond energy values. So for this purpose, we have seen how to do that. But let's open a past paper question. The most recent one from the May-June exam of 2023. Now look at this question. They give you the example, information. The question is about the energy changes that take place during the chemical reactions. Nitrogen reacts with oxygen to make nitrogen monoxide. The reaction is endothermic. Draw the axis provided on figure 6.1. Axis, reactants, products, enthalpy change, activation energy. It's a 5-mark question, free of cost. So this is in endothermic. In the case of endo, remember, reactants have a lower energy, products have a higher energy. So we'll make reactants here first. Let's write the axis. That's energy on the y-axis. Progress of reaction here. So these are the reactants. The better way is you can write reactants here. You can write that. But better way is to write the actual reactants. So that would be N2 plus O2. Since it's an endo one, the products will have a higher energy. What's the product? 2NO. So we've got 1 mark here, 1 mark here, 1 mark here. Congratulations. How to get the other 2 marks? The energy is being added. So the arrow will go upwards from the reactant and we are going to label it as enthalpy change of the reaction. And this is a positive value. Now activation energy, it always starts from the reactant. So we'll just shift it upwards here. The arrow goes here and this is the activation energy, again positive. And that is how you easily get 5 marks from this question. How easy is that? So that's one question normally occurring from this chapter. Now let's talk about this one. Again, this is an easy one. As I told you, they sometimes give you the bonds themselves and they have not given you any extra bond value. Just what it is. Now, enthalpy change, it can either be positive or negative. How will you find it out? By this calculation. In the previous one, the methane one we just did hypothetical. We didn't put in the values. Now we're going to add the values. These are the reactants. So enthalpy associated with bond breaking. So obviously these are the reactants. We're going to break this bond and this bond. So just simply we'll add HH plus BR. We'll just add these 2 energies. Put the values there. 436 plus 193. Let me open the calculator here. That's 629. I have occupied a lot of space here. Let's make it a smaller one. Because the 3 mark question, 1 mark for this, 1 mark for energy associated with bond making. Now we have the energy of HBr, but 1 HBr. There are 2 hydrogen bromides involved here. So what are we going to do? 2 into HBr. That's it. So 2 into 366. That would be somewhat close to 700. 732. So now you just put the formula. What was the formula? Enthalpy change equals to enthalpy of reactants minus enthalpy of products. So reactants have 629 and the products have 732. So we'll just do the maths. And the answer will be, let me check if it's the right one, 436 plus 629, 366 into 2, that's perfect. 732, that's a negative 103 value. So this is an exothermic reaction, students. That is all what you need to do. Sometimes they will give you the enthalpy change value and you'll have to find out the value of either of the reactants. Again, not that difficult. So that is all for today. I hope this lecture cleared your concepts regarding chemical energetics. So thank you so much for being here with me. Allah Hafiz.